Hello, my dear students. Please subscribe our YouTube channel for more free video lectures and click on bell button for notifications and visit our website to purchase full course.
Let us do a few more problems on probability. In that, I shall read out question number 3, which reads: a culvert has an expected life of 50 years and is designed for a flood magnitude of return period of 100 years. The risk associated with this hydrologic design is how much? That is what he's asking. So here the culvert has an expected life of 50 years and it is designed for a flood magnitude of return period 100 years. So here the flood is the event. So this event under problem number 3, let us see the solution. The return period for this event that is specified is 100 years. 100 years means it is very rare phenomena. Once in 100 years is probably the life of any structure, more or less, right? So that is the return period. What we have to find out is the risk. The hydrological risk is how much? So what is given is the return period. So based on the return period, we can calculate the probability of this event occurring once in a given year. Okay, at least once in a given year, that is given by the inverse of the return period, that is 1 by 100, which comes to 0.01. The probability of this event not occurring in the given year is 1 minus p, that is 1 minus 0.01, this is 0.99. So what we want is the risk. Therefore, the hydrologic risk is given by that is, this is nothing but p once in n successive years is 1 minus q to the power of n. As we have earlier mentioned, that is the risk associated with the design. So let us see how much is the risk. Here n value is given as, n value is mentioned as 50 years. That is the lifespan of the structure. So once in 50 years, that is what is the frequency that we have to work out. So this risk then is equals to 1 minus q is 0.99 to the power of 50. Now that becomes the hydrologic risk in the design. This value works out to 0.395 or 39.5%. Depending upon what is mentioned in the problem, depending upon the choices, as a multiple choice question, either the fractional values are given or the percentage is given. So depending upon that, we can mark the answer for that question. Okay, so you can copy this solution. Okay, let us now do one more problem. That is question number 4. I'll read out for you. That is, determine the recurrence interval using Hazen's formula for maximum and minimum rainfall for the following data for a 16-year period. Right? We have to find out the frequency. We have to find out the recurrence interval based on the given data. So let me just write down the question number 4 for you, and the rainfall values that are mentioned, rainfall values in millimeters as given as 508, 613, 359, 775, 677, 489, 637, 809, 859, 704, 638, 698, 642, 549, and 562. These are the rainfall values given, and we have to work out the recurrence interval or the frequency of the maximum and minimum rainfall. So what is required is the frequency or the recurrence interval of the maximum and minimum rainfall. Okay, that is what is required. So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 values. It's a 16 year period, so the intervals would be 15. That's the reason why we have 15 values here, right? So now if you look at this, what we need to do is, as I have mentioned earlier, we have to arrange them in the descending order. Okay, in the descending order, and we have to find out with that the return period for these two rainfalls, which is maximum and minimum. Maximum means the severest of the rainfall, the top, and the minimum means that which comes under the at the bottom of the list. So instead of rewriting all the values, I'll just write down the first value, that is the maximum value. Okay, so the maximum rainfall based on the above data is, you can see here, the highest value from this series is 859 millimeters. Okay, this is the rank number 1, severest of the storm, whereas the minimum rainfall, it is from this 359 millimeters. Okay, so the number of years of record here, the number of years of record is 16 years. Not the values, it's the number of years of record, that is given as 16. So this rank of the storm will be 16. I guess I have mentioned all the values. There should be 16 values. There is one more value which I have actually not entered here, that is 618. So in all we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 years is 15 intervals, whereas you get, for each year you get one rainfall value. So we have 16 values here. So you can see here, of the 16, the rank of the maximum rainfall obviously will be 1, and that for the minimum rainfall it will be 16. Now, based on the Hazen's formula, based on the Hazen's empirical formula, which says the recurrence interval is n by m minus 0.5, where n is number of years of record, n is number of years of record, whereas m is the ranking of the storm. In the list, what is the rank of the storm? So this is the first one and this is the second one. For the first one, right, that is for maximum rainfall, for the maximum rainfall, now T equals to, T is the frequency. Okay, so T equals to n by m minus 0.5. So this is n is 16 years divided by m. For the maximum rainfall, ranking is 1 minus 0.5. So this 16 by 0.5, the return period will be 32 years, isn't it? The return period for this maximum rainfall comes as 32 years, whereas for the minimum rainfall, that is the lightest of the rainfall, the frequency or the return period or the recurrence interval can be worked out as T equals to n by m. Now m for this storm, this is the ranking of the storm, that is 16 minus 0.5. 16 divided by 0.5 comes to about very small value, very closer to 1, that is 1.03 years. So what does this indicate for us? What does this indicate? What do you understand from this? So this is only working out the values, but from this, what do you read? You have to read the solutions. It's not just doing some mathematics. We have to understand what we are doing. Now, how does this help? How does the answers help? The answer for the first bit is 32 years, whereas for the second bit it is around 1 year, almost 1 year. So what does it help us understand? So we can say that wherever we are, whatever region we are considering, let it be any catchment, let it be any place or region, right? In that particular region, this rainfall of magnitude 859 or more, it can be more than 859 also. So this rainfall can occur once in 32 years in that particular region. Now, the idea that I get, right, the inference that I make out of this solution is that the severest of this storm as per the given list, that means in the past 16 years, there have been a maximum rainfall of 859, whereas a minimum rainfall of 359 millimeters has occurred. Now, this is the past record. Based on this, I can now predict that the rainfall having the highest magnitude will recur once in 32 years. That means once in 32 years, we can expect a rainfall of magnitude 859 millimeters or more, it can be any value beyond 859 also, will recur once in 32 years. So based on that, we can probably, this is the prediction, this is the probability. Whereas for that particular region, now we are not talking about generally for the whole country, it is only for a particular place or a region, or you can say a particular catchment. So for that particular catchment, a rainfall of let's say a magnitude 359 millimeters will occur once in a year, almost, because it is 1.03, it's hardly about 1 year and few days. And so we can say this rainfall will recur every year. So in that region, for that particular region for which this data is mentioned, in that region, a minimum rainfall of 359 millimeters or more will occur every year. Is it not a very good finding? Right? So we can now plan for the water resources. So in a particular region, if you are getting a rainfall of 359 millimeters at least, so with that depth of rainfall, we can do what we call it as water budgeting. The ultimate, now let me tell you now, because we are almost through the first topic, so first chapter rather, you should understand the ultimate objective of hydrology, as I mentioned in my first class, is development of water resources. In the context of development of water resources, we have to know how much is the input. The input is in the form of precipitation, in the form of a storm or a rainfall. So once we know how much rainfall is expected, because it's a probability. Once you know how much is the expectation of the input, then we can translate, then we can convert this input into storage. And that is what is hydrology subject teaches us. Knowing the input, we can convert this into output. This conversion of input to output is done by the catchment. So the job or the responsibility of a student of hydrology, or in general a civil engineer associated with or rather having specialization in water resources engineering, must know that it is the catchment which is going to help us develop more and more water resources. So for a constant input, how much maximum we can convert that into storage depends solely on the catchment. And hence, through hydrology, we shall propagate the importance of an area called as catchment. Okay, so this is, I would now ask you to copy the solution, please. Okay. So friends, let us talk about the abstractions from a rainfall. Abstraction means that which is deducted. Abstraction refers to deductions from the rainfall. As I have mentioned earlier, input is the rainfall, right? This rainfall is caught in a catchment. So after all the deductions, finally this water or the rainwaters reach the source where it is stored. The sources can be rivers, streams, lakes, ponds, reservoirs, something like that. Or it may also join the groundwater table. So after all these deductions, which we call it as abstractions, this rainfall is converted into storage. Okay, the various abstractions. Now let us write down. Before we discuss evaporation and evapotranspiration, let us briefly discuss these abstractions from rainfall. Abstractions from rainfall. Okay, the various abstractions from rainfall are, let us list out. Number one, it is interception loss. Some are losses, some are some get stored in some form or the other, but it is a deduction from the main precipitation or the rainfall. The second one is evaporation. All abstractions means it is losses only. Transpiration, number four, evapotranspiration. Evapotranspiration, which is combined evaporation and transpiration. Okay, and the last one is infiltration. So finally, we have in the calculations, what we have is some values, a few parameters or the few values of the parameters, including the rainfall, the runoff, the evaporation, the transpiration, evapotranspiration, infiltration. With all this, finally we will know precisely as to how much waters I am able to conserve, how much waters I am able to store in a source from a given rainfall. Knowing that this much rainfall is going to occur this year, with the help of probability or the predictions, we can assess fairly accurately how much water or sources we have in our source. By that we can plan the allocation of this water, which is still a probability. It has not yet occurred, the rainfall has not yet occurred, but even before the rainfall occurs in the monsoon season, mainly we can more or less accurately we can make out, we can determine, estimate the amount of water that we will have for the future period of 1 year. Okay, in that context, we have a method, we have an equation called as water budget equation. In that, all the hydrological events, I won't say hydrological events here, but all this will appear in that equation. From that, we will know how much waters we will be able to store in the source. Now, let us take it up one by one. Let us know what is interception loss. Interception loss. What happens is, on the ground we have lot of buildings. Okay, we have buildings, and we have trees, we have vegetation. Okay, so when the rainfall occurs, when the precipitation occurs, what happens is, the leaves of this plants, trees, or the vegetation in general, or even the buildings, they trap water, they intercept water, they obstruct the rainwater to touch the ground, right? So the water stays on the leaves of these trees, plants, or the vegetation. This will stay here on this. Okay, the same water, without really coming into the contact with the ground, evaporates. Okay, so some part of the rainfall, now this is the rainfall, some part of the rainfall doesn't actually practically reach the ground, and it is evaporated back to the atmosphere. This fraction of rainfall is termed as interception loss, because this fraction finally evaporates back to the atmosphere without reaching the ground. Okay, that is termed as the interception loss. So can we write a small point about interception loss, which I will dictate? Okay, please write down. The rain that is intercepted, the rain that is intercepted by tall objects, such as buildings, trees, etc. Tall objects such as buildings, trees, etc. along with the vegetation, does not reach the ground, and is evaporated back to the atmosphere, This loss is known as interception loss. This loss is known as interception loss. Next point. This loss is maximum at the beginning of the storm. This loss is maximum at the beginning of the storm. Next point. Interception loss which is a part of initial loss, which is a part of initial loss, is so small that it is neglected, in the hydrological analysis. analysis. Okay, you can see the plot also. It's an asymptomatic curve between interception loss versus time. As I have mentioned, it is initially high at the beginning and later it decreases as shown in the curve. This is asymptomatic killer. You can note down the plot so that we can write a line on this also. You can mention now, you can mention the relation after this curve. You can mention the relation between the interception loss and time. The relation between interception loss and time is asymptomatic. Meaning it takes a large time, or rather it takes a long time, meaning it takes a long time to become zero. So that is something about interception loss. After this, we shall take up the topic, that is evaporation. You can also note down the topic, and we shall now discuss as to what is evaporation, its definition. We shall also have a discussion on the various factors, maybe physical, chemical or meteorological, which will affect this process of evaporation. Evaporation as such is a very important part of hydrological cycle. It is the link between the rainfall, rather, I won't say direct link, but it's a link between the atmosphere and the ground storage. That means the surface storage. The quantum or the quantity of water that escapes into the atmosphere directly as a loss is very, very significant, is very, very high. In fact, if you see the number, if you see the magnitude of evaporation, it also exceeds the annual rainfall value, especially in the context of India or maybe the tropical regions in general. Evaporation magnitude is more than even the magnitude of rainfall. So we have to understand this process very closely so that we can evaluate the storage. In the sense, we can analyze this water budgeting. Let me repeat, hydrology, finally the bottom line of hydrology is to write the water budget equation or to understand water budgeting. Water budgeting means how much we are able to receive, how much we are able to store, and how much we are able to utilize for our for our consumption. In the sense, how much water we can allot to irrigation, how much water we can take as a part of water supply, how much waters can be used for generating hydropower. So different applications we can allocate based on this water budgeting, and this water budgeting requires in-depth understanding of all the abstractions that I have listed just before this, in addition to the rainfall. Rainfall is the input, and the abstractions also need to be calculated properly, accurately, so that water budgeting can be properly done. Now, let us try to define what evaporation is. Of course, in physics, evaporation is the process in which the water changes from liquid state to the vapor state. Now, this is the fundamental understanding of the process of evaporation. It is just a change of state. Okay, evaporation is nothing but the change of state. The simplest of the understanding, but for an engineer dealing with water resources, the understanding of evaporation doesn't really end with this. Here it's defined only as a process, but how does this process affect our water resources? Okay, that is what we are going to study now. So we can define this as, or rather it can be expressed. Now look here, this is more technical, expressed in terms of depth of water that has escaped from a given area in a given time. Again, it is the depth of water that has escaped from a reservoir. That is what is the definition of evaporation. So when you say per unit time, the units can be, units of evaporation can be millimeters per hour, or it might be centimeters per month, or centimeters per year. Since the rate of evaporation is very, very small, very, very less compared to the intensity of rainfall, right? So the appropriate units would be in terms of millimeters per day, millimeters per month, millimeters per year, because it's a slow process basically. That is what is the understanding of evaporation for a student of water resources or in particular hydrology. To understand evaporation closely, we have to understand the law of evaporation as given by Dalton's. Let me write down the Dalton's law of evaporation. He has correlated certain parameters associated with the atmosphere, nothing but the meteorological parameters, based on which evaporation loss may be worked out. So according to him, according to Dalton's law, the evaporation loss, now we will write it as E with the subscript L. L stands for loss, E stands for evaporation. Okay, so evaporation we shall indicate it as E. As we have used the uppercase or the capital letter P for rainfall or precipitation, the capital letter E will now stand for the evaporation depth. Okay, so the evaporation loss according to this law from a water body or a lake, according to Dalton, he has studied the evaporation from a water body called lake. So the lake evaporation is directly proportional to the evaporation loss from a lake is reported as by this scientist as the the difference in pressures, between two values, okay, PW and PA. Okay, that is the Dalton's law. Before writing this, let me dictate the law. Please write down the statement of the law. According to this law, or before I dictate, then friends, kindly copy this before we write this law. Kindly copy what I have written on the board. Then I'll dictate this statement of the law. Okay, having written this, now you can write down the rate of evaporation. I'm giving the statement of this law, please. Please write down the rate of evaporation from a water body. The rate of evaporation from a water body is equal to the pressure difference is equal to the pressure difference between the saturation vapor pressure at the level of water surface, saturation vapor pressure at the level of water surface, and the pressure in the overlying air, overlying air at a specified height. At a specified height. So that can be expressed mathematically like this. So the rate of evaporation is proportional to this two pressure values. Pw is the saturation vapor pressure at the water surface, whereas this Pa is the pressure in the air at a certain height. Okay, that is specified height. So here we can rewrite it as, removing the proportionality, you get P minus Pa. This is the formula that is derived from the Dalton's law, where C stands for the constant for the formula that has been given by Dalton. Now, evaporation, in addition to the pressures, evaporation is also due to, it is aided by wind also. The more the wind, the higher the wind, the higher would be the rate of evaporation. So there is a small correction that is made. That's a wind factor is also included. The same formula can be corrected as C into Fw into Pw minus of Pa. This is because of the wind, where Fw is the wind correction factor. Knowing that evaporation is not just due to the pressure difference, but it is also aided or helped by the wind. So there is a small wind correction factor that is also included at a later stage. Okay, so you can write this, and after writing this we will do some small observation we can do in this formula. You can put a star and write down evaporation continues until Pw is greater than Pa. It's obvious, as long as the pressure difference is positive, that means evaporation will continue. The pressure at the water surface shall be higher than at a certain altitude. As you go up, a certain value of pressure will take specified height, and the pressure difference, as long as the difference is positive, evaporation will continue. And when Pw becomes equal to numerically, or both the pressures, if they are same or equal numerically, then evaporation stops. This is obvious from the formula. Now the interesting element of this formula is what happens, right, when Pw is less than Pa. When the pressure at the water surface level drops below the pressure in the air above, what will happen? So if you see the mathematics here, this value in the bracket would come as negative. And what does negative evaporation indicate? Negative evaporation means the reverse process of evaporation. So evaporation is from liquid to vapor stage. So the reverse of negative evaporation is from vapor to liquid. Vapor to liquid is condensation. So we can write here, when PW is less than PA, condensation occurs. Condensation will occur. So this is what is the observation that you can make out from the Dalton's law. Let us now discuss briefly the various factors affecting evaporation. The various factors affecting evaporation include the radiation, the sunlight. Radiation means sunlight. Then the temperature, then the wind velocity, the atmospheric pressure, the humidity, the quality of water. There are many. I'm just listing out a few of them. Then you can also include here size of the water body and so on. I have listed the more important of these. Even the depth of water also affects the evaporation rate. Okay, but anyway, coming to this, first one, radiation. Evaporation is directly proportional to radiation. Here, evaporation, when I say evaporation here, it's the rate of evaporation. So the rate of evaporation will be faster if there is lot of radiation energy available in the atmosphere. If the sunlight is very strong, that means the energy of the sun, that is radiation energy, is very, very intense, and that causes evaporation to happen faster. So it's directly related. Temperature. Okay. If the surface temperature increases, evaporation rate also increases. So E here is proportional to T. Directly proportional means as the temperature increases, evaporation rate also increases. Third one, you can see the wind velocity. Wind velocity. Evaporation is directly proportional to the wind velocity. The faster the wind is, if the wind speed is high, as I said, it will help evaporation process to run faster. Hence, it is directly related to that. Number 4, atmospheric pressure. Atmospheric pressure. Here, if evaporation rate is inversely proportional to the atmospheric pressure. That means if the pressure is low, evaporation rate will be high, and if the pressure is less, evaporation rate will be more. Vice versa. If the atmospheric pressure is increases, evaporation rate decreases. So that's an inverse relation between evaporation and atmospheric pressure. Number 5, humidity. Right? Humidity also is inversely related to evaporation. Higher the humidity, lesser would be the evaporation. So as the humidity increases, evaporation rate decreases, and vice versa. So in this session, we will stop here and continue discussion on the same in the next session, wherein we will discuss the remaining factors affecting